Hello everyone, I'm Chi-Ning from Harvard. Today I'm going to talk about recent work with Boaz and Xun on quantum supremacy. Okay, so let me start from the motivation. So the motivation is about extended Church-Turing thesis, which asserts that any feasible efficient computation in the physical world is in BPP. Okay, but this is like the hypothesis we are working on. Yeah, but but does this really true? Like, can any realistic model solve a problem beyond BPP? For example, like quantum computation could be a very legitimate candidate to refute extended Church-Turing thesis in the sense that we know that factoring can be solved in BQP. And while factoring, most experts believe that it is beyond BPP. Yeah. But in the meantime, BQP is a theoretical model. Does BQP really realizable in the physical world? Yeah, if so, then the extended Church-Turing thesis will be refuted. Can this really happen? Yeah, so can quantum computation really break the extended Church-Turing thesis? Yeah, so if we want to use quantum computation as a program to refute the extended Church-Turing thesis, maybe like trying the Schur's algorithm in solving factoring would be the most promising way. But the issue is like to really demonstrate the computational power of quantum. Using factoring, it requires many qubits, and this is a little bit far reach from the current technology. Yeah, and also before we really realize such quantum computation solving this important computational problem, yeah, it also could be the case that there are some fundamental physical barriers to build a quantum computer. For example, for most quantum skeptics, yeah, like the noise stability or the error correction issue in the quantum computer might be a fundamental physical barrier to really achieve scalable quantum computation. Yeah, meaning that maybe BQP just is simply a theoretical model. This BQP actually cannot be really achieved in the real physical world. Yeah. So if people really want to test whether quantum computer is feasible, it's like if extended Church-Turing thesis maybe is wrong, yeah, then can we demonstrate it using near-term technology instead of like waiting like until 2000 more than 2000 qubits can be implemented? Can we demonstrate this with a near-term technology? So this is where quantum computational supremacy comes a role. This is like a compromise between theory and experiment. Yeah, so in the theory side, we have lots of advanced and interesting non-trivial quantum algorithms. Yeah, in the past 10 or 20 or 30 years. Yeah, on the practice side, in experiments, recent years, there are many exciting results from big companies like IBM, Google, or the recent Chinese group. Yeah, people can roughly build like about 50 to 60 number of qubits. Yeah, but most of the theory side, the algorithm there requires much more number of qubits. So in the quantum supremacy program, the proposal is to refute extended Church-Turing thesis in a NISQ system, the noise intermediate scale quantum system. So in a NISQ system, maybe the number of qubits just about like 50 or 100. Yeah, and there are many popular candidates like random circuit sampling, boson sampling, or IQP. Yeah, trying to propose a program, yeah, like it's possible to demonstrate to refute ECTT using just maybe 100 number of qubits instead of waiting for 2000 qubits. Okay, and in this talk, we are going to focus on a specific approach called random circuit sampling. So this is the approach used by Google. Yeah, and we are going to study the theoretical foundation of this approach. Okay, And before introducing what random circuit sampling is, let me remind everyone with some basic of quantum circuits. Yeah. So the introduction here will be very preliminary and it should be sufficient for understanding the rest of the talk. Yeah. So in quantum circuits, there is quantum state, and n-qubit state you can simply think of it as the length 2 to the n unit complex vector. Okay, and the quantum gate is simply a unitary operation acting on an n-qubit state. Yeah, and a 2-qubit state is like a partial, a partial unitary applying on this 2 to the n unit complex vector, where the rest is applied by the identity. Okay, and a quantum circuit is like a sequence of quantum gates composed with certain ways. Yeah, and you can also think of a quantum circuit as 2 to the n by 2 to the n unit actually in the end. So so the application of quantum circuits on input state design is just like applying a 2 to the n by 2 to the n unitary matrix on a 2 to the n unit complex vector. So the result is still a 2 to the n unit complex vector. And because this is a unit vector, so it is we can naturally define a distribution from this the resulting output vector. Yeah, and the distribution is over all the n bit strings. Okay, and the probability density is simply the square of the absolute value. Okay, so now we have this basic notion set up. We can describe what is the random circuit sampling approach to demonstrate quantum supremacy. And this is exactly the approach used by Google's very recent breakthrough. Okay, so in the random circuit sampling approach, it is convenient for us to think of it as a game. So there are two players. One is the challenger. You can think of it as quantum skeptics. And prover, for example, you can think of it as Google. Yeah, so the challenger will randomly select some gates. Yeah, so this is just some small unitaries. And maybe also pick an input state. And with a lot of generality, you can think of it as the zero state. And then the challenger sends these things to Google. Okay, and the prover then try to simulate the circuit, because we assume in an honest setting, the prover is able to really run a quantum computer, so it can simulate the quantum circuit. So furthermore, it can be able to sample the output string from output distribution QC we defined in the previous slide. So the prover samples many strings from this output distribution, and then sends back to the challenger, and the challenger want to verify that the samples does indeed follow the output distribution Q sub C. Okay, so intuitively, why this approach makes sense. So for example, if the prover has a quantum power, then we can imagine that it is very simple for it to simulate the circuit. So it can indeed sample some strings from the output distribution Q sub C. However, if the prover doesn't have the quantum power, yeah, intuitively, the best way, the simplest way for it to achieve this is to simulate the whole circuit with a classical computer. And we know that the trivial way to simulate a quantum circuit using classical computer will take exponential time. So this probably is not achievable. Yeah, but in order to really make some, to make this reasonable, we need to properly define what do we mean by verifications here to make everything making sense. Okay, so to verify, so in this, if once we think of it as a computation again, yeah, we probably want a verification process to satisfy a few properties. Yeah, first, we might want the verification process to be efficient, such that we can demonstrate quantum supremacy in a reasonable amount of time. Yeah, because we wouldn't want the changers to, fully simulate the circuit in order to verify this. This might be too inefficient. And we also want completeness, meaning that if the prover does sample strings from the ideal distribution Q sub C, then the challenger should bear a set with high probability. And also soundness, like if the sample is coming from a classical device, then we want the challenger to reject with high probability. Okay, so given these criteria, one of the popular verification process people are using, like Google is using, is called this linear cross-entropy benchmarking. This is a specific statistical quantity. Yeah, and the definition is as follows. So definition of linear cross-entropy benchmarking, abbreviated linear XCB, is defined with respect to two things. One is the circuit C, and another is the probability distribution over n-bit string P. So the linear XCB of P with respect to C is defined as the following expectation. So it's the expectation of you sample from this distribution P and apply like the ideal distribution Q sub C of X and multiply by some normalizing term. Yeah, and this is the resulting linear XCB of P respect to C. So to see whether this satisfies the previous criteria, let's take a look. So on the efficiency side, actually it doesn't. So notice that to really calculate or estimate the linear XCB of a distribution P, you need to calculate Q sub C. Yeah, so this actually takes exponential time. So this is one that drawbacks. But as if the circuit is small, this maybe is doable, still in a reasonable amount of time. Yeah, and on the completeness side, yeah, when we really sample, when a prover really samples from Q sub C, meaning that here if P is replaced with Q sub C, yeah, and actually this is provable that when C is random enough, yeah, then the linear XCB will be 1 with high probability, or almost sure. Okay, on the other hand, if P is a uniform distribution, then people can show that actually the linear XCB should be close to 0. Yeah, and this good property is guaranteed by the property, the so-called anti-concentration of a quantum circuit that guarantee you such a separation on this specific statistics. And this linear XCB is then used by like Google or other people to demonstrate quantum supremacy using the random circuit sampling approach. Okay, so after defining random circuit sampling and their verification process, the linear XCB, let us take a look at what Google did. So in Google's quantum supremacy, in their Sycamore chips, they work on the 2D nearest neighbor circuits. So you can think of that they arrange the qubits in a specific way, as indicated in this figure. And the number of qubits about like 12 to 53. Like this is the best they can do at the moment. And the gate is adding in a very specific way. Like in the blue part, they add gates like in different layers. And the gate is also chosen from certain ensembles. And in their experiments, they are able to run the depth from 14 to 20. So at most, they can run for depth 20. So it's like 20 layer of depth. Okay. And using this, they want to show that their quantum simulation of such circuits with such a random gate set, this specific structure, they can achieve high linear XCB. And in the meantime, they also assert it is impossible for a classical computer to achieve such high XCB. So what they really achieve is the following. So unfortunately, because the things I mentioned before, like the verification actually is exponential time. So what they really actually can do is like for depth being 14, they are able to simulate up to 53 qubits, and they get a line on the left. And for the deeper circuits, they only extrapolate, from their result of shallower circuits. And they are able to claim that when the number of qubits is 53 and the depth is 20, they extrapolate and get the linear XEB value from their quantum simulation is able to achieve like 2.24 times 10 to the minus 3. So this looks small, but what they claim is like for any classical sampling, it will take like 10,000 years to achieve this. Okay, and this 10,000 years estimation basically is from like the classical computer has to fully simulate the quantum circuit. Okay, so does Google really refute extended church Turing thesis? Yeah. So in our opinion, their classical harness is not very solid. Like the 10,000 years estimation is based on like fully simulations. And also immediately after they announced their result, other groups such as IBM and Alibaba, they also plan to have a faster classical simulation. Maybe can achieve the similar things within 2 weeks or few days. And to us, the more important thing is like the verification process they're using, the linear XED, is not very well studied. It is. There could be a chance that linear XED is much easier than full simulation of a quantum circuit. And another drawback is also like their verification is too inefficient, so their results basically is based on extrapolation. So it is hard to imagine if they want to scale up to even more qubits. In this talk, we are going to focus on linear XED, their verification process, and try to give a more solid theoretical treatment. Okay, so to study linear XED, we started from the perspective of attacking linear XED in the sense that the Google's belief is like if you want to achieve high linear XED, what you really need to do maybe is to fully simulate the whole quantum circuit. But is that possible to leverage the structure of the circuit and the definition of linear XED so that we can still achieve high linear XED without fully simulate the circuit? But there are two difficulties. Really want to make this happen to spoof linear XED. Theoretically, this is not very easy to analyze. Like the quantity, although is properly defined, but it's in general hard to analyze for an arbitrary circuit. And also experimentally, if we want to demonstrate there is a classical algorithm, the verification process is also difficult to do, as I mentioned before. So this is like in the awkward situation that if you want to demonstrate if you want to spoof Google's experiments, you first need to have a very powerful machine. So maybe you need to even use Google Cloud to refute Google's quantum supremacy. But anyway, in this work, we are mainly focused on the theoretical side. So our main idea is to try to see if it is possible not to fully simulate the full circuit, but also get a non-trivial linear XED value. And our observation is the following: we observe that the marginal of an output qubit only depends on its light cone. So actually, this is a very basic fact of quantum circuits. So what is a light cone? So light cone of output qubit 1 is the red part, which is like the gate or the input qubit that has a path to this output qubit. So in this example, there is a 6-qubit quantum circuit, but the light cone of the output qubit 1 is only 4. So in order to calculate the marginal probability of just this output qubit, we only require like 2 to the 4 times, like 2 to the light cone size, instead of 2 to the n, like here it's like 2 to the 6 times. So in general, for DEFD circuits, because we only have 2-qubit gate, so for DEFD circuits, we know that every light cone is of size at most 2 to the d. So actually, for each output qubit, we can calculate the marginal in time 2 to the d. So when d is very small, meaning that we are in a shallow circuit region, we are able to calculate the marginal of each output qubit very efficiently. So intuitively, if we can use this such marginal of each output qubit to perform some bias sampling and analyze whether this achieves high linear XEB, then we might be able to discover a classical algorithm that achieves non-trivial linear high XEB without fully simulate the circuit. Okay, so let's try to put this idea more concretely, like describing a classical algorithm, what we are meaning. So the classical algorithm can be worked as follows. So we first pick some output qubits where their light cones are disjoint and of size L. So in a DEFD circuit, this L is just 2 to the d. And then we can calculate the marginal of each output qubit in time 2 to the L. And then we can use this marginal as information to sample the output strings biasly. So for those output qubits being chosen, we sample according to the marginal, and then we sample the rest uniformly. Yeah, so intuitively, because we sample the output qubits some output qubits following their marginal, so the final distribution we are sampling might have some non-trivial correlations with the underlying ideal distribution Q sub C. Yeah, but in order to really demonstrate this algorithm is non-trivial, we need to have either theoretical analysis or empirically demonstrate the performance. Yeah, and in this work, we focus on the theoretical side, and we have the following results. So we show that the previous algorithm, the algorithm described in the previous slide, is the first non-trivial classical algorithm that had achieved non-trivial linear XEB value in the shallow circuit region. Yeah, so our main theory is stated as follows. So let's see the n-qubit DEFD circuits, and the light cone size is at most capital L. And all the gates are hard random, so this is also a reasonable assumption in the theoretical analysis. And the algorithm will output the distribution P in time, polynomial in N and 2 to the L, and achieve linear XEV value being the following. So this is a little bit, maybe not easy to see at first scan, how does this scale? So let me give you a corollary instantiated to Google's 2D circuit. So in their 2D circuit, if the depth is log n, then our algorithm is able to output the distribution in time 2 to the d square. So this is some kind of quasi-polynomial time, and achieve one inverse polynomial linear XEB. Yeah, so this is far better than what they can, because the classical hardness people usually claim for the random circuit sampling approach is that they cannot achieve even like 1/2 to the n linear XEB. So here we can even achieve 1/poly n. But the drawback is like here we are only able to prove the algorithm or to implement the algorithm on a shallow circuit. Okay, so let me briefly explain what's the intuition underlying the algorithm and our analysis. Yeah, so the key ingredients in our analysis is treating linear XEB as a random walk. So we give a random walk picture of linear XEB in the sense that we show that the expected value of linear XEB over the random gates can be written as the summation of some tensor networks, non-negative tensor network indexed by random walk path. Yeah, so it's like we can write the expected value of linear XCB in the big exponential sum, where all the summands they are non-negative, and it is indexed by path of the circuit. Yeah, so with this random walk picture in mind, Google's noisy simulation of quantum circuits can be viewed as there's some small noise for applying on each gate. Yeah, so the summands will become slightly smaller for all of them. Yeah, and hence that's why their linear XCB value is a little bit smaller. It's actually scales as like 2 to minus d, because the noise aggregates in, like across depth. And for our algorithm, or Lycon algorithm, you can think of it as we put very large noise on the output qubit we are not choosing. Yeah, so it's like for those paths that touches those non-chosen output qubits, it's like that summand doesn't being counted. Yeah, but for those paths that touches the output qubits we chose, then that part will be counted. So then for those part, if we have enough output qubit being chosen, that then it means that we actually have a large number of summations in this random walk picture, so we are able to achieve higher expected linear XCB. Okay, so how to interpret our result? Yeah, so our result is basically as far as we know, it's the first classical algorithm that are very specifically designed for linear XCB. So this shows that to achieve high linear XCB, you might not necessarily to fully simulate the whole circuit. Yeah, it's possible that you're just using some easily computable statistics and get higher linear, non-trivial linear XCB. Yeah, and also from the random walk picture, we can know that actually the noise is quite subtle, because we know that Google's quantum simulation is also noisy, so that's why they cannot get linear XCB very close to 1. So maybe their noise is inherent, and it is too large, and actually it is able to achieve comparable linear XCB in a classical device. So actually we have some ongoing work trying to advance our algorithm on that. And on the more technical side, yeah, our random walk picture for linear XCB could be also of interest to get people understand more what's this verification process really does. Yeah, because this is like kind of like a trade-off where we want to have verification, but it should also be efficient, but also have the completeness and soundness property. Yeah, and linear XCB is the one being chosen, but maybe it's not appropriate. So to have more understanding on that is very important, and the random walk picture might give more insight on that. Good. So let me summarize our work with some future directions. So I think there are 3 important directions, actually very different directions, but all of them are important, and it requires both theory and experiments. Yeah, and on the theory side, it is important to have more understanding in linear XCB, because this is like the computational like verifications people are using. Yeah, so the hardness is really based on linear XCB being hard for a classical computer to achieve. Yeah, so if you really want to demonstrate like extended Church-Turing thesis can be refuted by quantum computation, it is also of the same importance to understand linear XCB better. And on the experimental side, yeah, of course, it is important to scale up the quantum computer for sure. And but also the faster verification and trying to see what's the limit of classical simulations also of the, I mean, of the same importance in my opinion. Because if you because as I mentioned before, the parameter regime actually is quite subtle, because in a quantum simulation there's some inherent noise, and the whole program of quantum supremacy basically is to understand, is this noise is inherent? Is there really a physical barrier to achieve large scale like noise tolerance quantum computation? So to see if there's a comparable classical simulation, like for the same quantum supremacy test, is important for us to see whether the current quantum technology already breaks extended choice thesis or not. And the third direction, which I think is also very interesting, is to propose new quantum supremacy protocol. So the random circuit sampling protocol now suffers from the limit of verification. Like the verification is inherently exponential. So can we come up with a better quantum supremacy protocol with a more scalable verification process, and also have a more solid complexity theoretic foundation? Yeah, and we also have some work toward this direction. Okay, so yeah, so to summary, yeah, I think quantum supremacy is indeed a very exciting area, like between in the intersection of like experiment and theory, intersection of physics and computer science. And so currently it looks like the experimental side is leading. There are lots of breakthrough in that. However, the theoretical foundation and understanding in this quantum supremacy is very lacking. So it will be very interesting if there are more serious study in this and give a more solid foundation on this, so that we can see whether it is possible or not to refute or not refute extended Church-Turing thesis in the near future. Okay, so this is my talk, and thanks for your attention.